Welcome to This Explainer. Today, we're going to look at a real unlikely hero in the world of machine learning, the naive Bayes algorithm. You know, when we talk about artificial intelligence today, we usually picture these massive, incredibly complex neural networks that need literal supercomputers just to turn on. But what if I told you that one of the fastest, most efficient learning algorithms we have is basically the mathematical equivalent of a reliable old packet calculator? It's built entirely on a surprisingly naive assumption, which creates this fascinating paradox that we're going to unpack right now.
So think about a universal problem we all deal with every single day: classification. Your inbox is constantly bombarded with spam emails practically screaming free, winner, or offering you millions from a distant prince. But mixed in there are the real crucial emails from your boss or your family. How does a computer actually decide what's what? Well, instead of memorizing rigid rules, naive Bayes uses this really sleek system of calculated probabilities to figure it out. Here's our agenda for today. We'll start with the paradox behind its name, break down exactly how it works, explore its three main variations, check out some real-world applications, throw it into a showdown with other algorithms, and finally talk about its future.
Let's kick things off with Section 1, the paradox, or what's in a name. We're going to see how this algorithm builds its entire foundation on two wildly contrasting ideas.
The first half of its name comes from Bayes' theorem. This is a mathematical formula that calculates the probability of an event based on prior knowledge. Essentially, it uses what we already know to figure out what we want to know. So in our spam filter example, Bayes' theorem is basically asking, okay, what's the probability that this new email is spam given the specific words it contains? It is a highly logical, completely mathematically sound way to look at the data. But then we get to the naive part, and this is where things get a little weird. The algorithm makes a massive, seemingly foolish assumption. It assumes that all input features are completely, 100% independent of each other. Think about a piece of fruit for a second. If we want to classify a fruit as an apple or an orange, naive Bayes assumes that its color, its size, and its weight have absolutely nothing to do with each other. In the real world, obviously, size and weight are connected, right? A bigger apple weighs more. But this algorithm, it completely ignores that reality. It treats every single data point like it's in a vacuum, as if they've never even met.
Moving right along to Section 2, the mechanics. How does it work? Let's figure out how this naive hero actually pulls off complex classification while completely ignoring how things relate to one another.
It basically boils down to four highly logical steps. First, we collect training data. We gather thousands of labeled examples, like tons of emails already marked as spam or not spam. Second, we learn the feature probabilities. The algorithm calculates how often specific features, like certain words, appear in each class. It's going to quickly notice that the word winner shows up way more often in spam. Third, when a brand new, unseen email arrives, we apply Bayes' theorem. We calculate the probability of each possible class based entirely on the words in that new email. And finally, we compare those probabilities. The algorithm just looks at the math and picks the winner. If it's 80% likely to be spam and only 20% likely to be real, boom, it goes straight to your junk folder.
All right, Section 3. Three types of algorithms. To really understand how adaptable this thing is, we need to look at the three distinct flavors operating out in the wild.
Depending on what your data looks like, you've got three distinct options. First is Gaussian naive Bayes. This is your go-to for continuous numerical data that follows a normal distribution. Think medical stats like age, height, or blood pressure. Next up is multinomial. This one handles discrete count data, making it the absolute undisputed champion for text classification, like counting how many times a specific word appears in a massive document. And finally, we have Bernoulli. You use this when your features are strictly binary. We're talking yes or no, true or false, 1 or 0. Super efficient for simple stuff. Which brings us perfectly to Section 4, real-world applications. The versatility of those three types is exactly why this algorithm is used across so many different industries today.
Naive Bayes is literally everywhere. In email services, it's the backbone of your spam and phishing detection. In banking, it's quietly calculating risk and flagging fraudulent transactions. In search engines and social media, it's constantly running sentiment analysis, trying to figure out if a movie review or a tweet is positive or negative. But let's look at healthcare for a second, because this is where it gets real. Imagine a hospital wants to predict if a patient has the flu based on symptoms like fever, a cough, and body aches. By crunching the probabilities from thousands of past patient records, naive Bayes can instantly give doctors a statistical likelihood, actually supporting vital, life-saving decisions in real time.
Okay, Section 5, the showdown. We'll look at pros, cons, and comparisons. Let's step into the ring and see how our unlikely hero stacks up against its rivals and where its armor actually cracks.
First matchup, naive Bayes versus logistic regression. Now, naive Bayes is incredibly fast and absolutely phenomenal for text classification, and it requires way less training data to get up and running. But logistic regression is more flexible because it actually learns the relationships between features. If your data features strongly depend on each other, if they're highly correlated, logistic regression is almost always going to perform better than our naive friend.
Next challenger, the decision tree. Here, naive Bayes wins handily on training speed, especially when chewing through massive text datasets. It spits out predictions almost instantly. But if you need to actually show your work, decision trees use concrete decision rules rather than hidden probabilities, making them way easier for humans to visualize and trace. Plus, decision trees are vastly superior when it comes to handling nonlinear complex relationships in the data.
And that brings us to its biggest weakness. That naive assumption of total independence, it's a very real limitation. Sure, it makes the math fast and easy, but it's often completely unrealistic in the real world. Because of this, naive Bayes really struggles with highly complex data where relationships are deeply intertwined. If you've got features that strongly rely on each other, more advanced algorithms are just going to beat it in raw accuracy, hands down.
Oh, and it also suffers from this really specific mathematical quirk known as the zero probability problem. Let's say a totally brand new word pops up in a spam email, a word the algorithm has literally never seen before during its training. Because of how the formula works, it assigns a probability of absolute zero to that new word. And since the algorithm multiplies all these probabilities together, one single zero wipes out the entire calculation. Literally, a single typo can break the math. To stop this from happening, data scientists use a clever little workaround called Laplace smoothing, which just adds a tiny baseline probability across the board so that a zero never crashes the whole system.
Finally, Section 6, the future of naive Bayes. Where does all of this leave our simple algorithm in the modern era of AI?
Look, we are living in the age of deep learning. Massive neural networks dominate the headlines every single day. Yet naive Bayes remains incredibly relevant. Why? Because it is so computationally efficient. It trains wildly fast using barely any resources compared to the big guys. It's still a powerhouse for natural language processing. And most importantly, because of its speed, simplicity, and low cost, organizations use it as the ultimate baseline model. It's the reality check. It's the standard you measure your multi-million-dollar complex AI models against to see if they're actually worth all that extra time and money.
Which leaves us with this final fascinating paradox. In an era defined by increasingly complex, resource-heavy AI, can trusting a mathematically naive assumption actually be the smartest solution in the room? Honestly, sometimes stripping away all the complicated relationships and just trusting the raw, simple probabilities is exactly what you need to cut through the noise. Thanks for joining me for this explainer, and I hope it really changes how you view the raw power of simplicity.